All right, let's start with the good news, the very good news. We have not covered there's one important factor that we have not covered yet, and that is buoyancy. So for problem set 9, we're gonna kick to problem set 10, number 2, 4, 6, 9, and 13. So that effectively eliminates almost half the problem set. Yay! We've done a lot of work today.
2, 4, 6,
9 and 13.
What about
We haven't covered, there's something called buoyant force. And since we haven't covered it in class, we're gonna come out of probably within the first 45 minutes of Tuesday's class, we'll cover it. But that won't give enough time for the class to figure things out. So what we're gonna do, all of these, well, what I'm gonna do is I'm gonna edit this and create a new problem set 10, and I'll just copy and paste the ones that we've just eliminated. And add a few more. Number 1. So water starts moving at 10 meters per second at the top of a hill at a pressure of 1 atmosphere. So this is the classic P1, 1 atmosphere. I'm gonna need to know P2 and V2. V1 is 10 meters per second. The change in height is 5 meters. Radius of the pipe at the top is 0.1 meter. So it's a circular pipe. Radius at the pipe at the bottom is 0.2 meter. Circular. What is the pressure of the velocity of the water at the bottom of the hill? Now I wasn't specific as to what units I want the pressure in. Let's just use atmospheres. So for something like this, it's a 2-step problem. First step, equation of continuity. A1 V1 is equal to A2 V2. Now they're circular, so pi r1 squared V1 is equal to pi r2 squared V2. So r1 squared V1 over r2 squared no V2. V2 is there. And there we go. So that's the velocity of the water at the bottom of the hill. All you got to do is use equation of continuity. The next thing is to use P1 plus rho g H1. The fluid inside is water. So 1,000 kilograms per meter squared plus 1/2 rho V1 squared P2 rho g H2 plus 1/2 rho V2 squared. All right, I'm looking for P2, the pressure at the bottom. So I'm gonna look for this. Now, for something like this, you need to figure out where your zeros are. And I'm gonna set the lowest point to have a height of 0. So H2 is equal to 0 and H1 is equal to 5. So H2 goes away. And I'm left with this. Now the one thing that we need to be careful about is I gave you the initial pressure in atmospheres. I'm looking for the pressure in atmospheres, but these terms here will provide answers in newtons per meter squared. So you have to do the conversion. That atmosphere is in the denominator of the denominator. It would get kicked up. Atmospheres and atmospheres will give you this pressure in atmospheres. And so all you got to do now is plug and chug the thing. And someone real quick, look up the density of gold real quick. Because in problem 3, we have $1 million worth of gold. And gold is $1,200 an ounce. So really this is a unit conversion problem initially. Now each ounce, 16 ounces to a pound, 1 pound, 16 ounces, and then 454 grams per pound, and then 1,000 grams per kilogram. So this will give you some number, the mass of gold in kilograms. Now the thing that I have to have is the density. So you don't have to give it to me now, but let's say the density of gold, just look it up, it's on Wikipedia. It's 19,300 kilograms per cubic meter. I think that's what it ends up being. So the density is mass divided by volume. You have the mass, so volume is mass divided by the density of gold. So take that number, divide by the density, and now you've got your volume in cubic meters. The question is, if the gold was shaped in the form of a sphere, what is its radius? Well, volume of a sphere is 4/3 pi r cubed. So V, or 3/4 times V over pi is r cubed. So r is the cubic root of 3V over 4 pi. So you have to get the mass first, divide by density to get volume, then take volume, plug it in there, and then do that math, and then you got it. So it's just it's a combination of geometry and density. No, I was messing it up. Yeah, but if you convert grams per cubic centimeter to kilograms per cubic meter, it ends up like this, which is what I need.
Why do you have meters cubed next to where you're getting velocity?
Where? No, this isn't velocity, this is volume.
Okay.
That's the unit.
Okay.
What's the subscript under ref?
AU.
Is that under 3 on the left?
This?
Yes.
That is a 3.
No,
It-
like, is that column number 3?
Yes. All right, number 5. You have a 100,000 liter water tower and you're going to drain it. So the volume is 100,000 liters. The pump can pull water out of the tank through a circular opening at a velocity of 10 meters per second. So this volume has straight lines. The lowercase v for velocity is a little more curvy. 10 meters per second. What is the required radius of the pipe so the tower can be drained in 4 minutes? So time 240 seconds. Now this deals with flow. So flow is area times velocity. Flow times time will give you volume. So volume is equal to area, velocity, times time. And we're looking for time. So volume over area, velocity is time. Now what you need to do is you need to take this 100,000 liters and convert to cubic meters, because we're going to be playing with meters as our length. So the volume in cubic meters is divided by, oh wait, no, we're not doing time. Area pi r squared, and we're looking for r, the velocity times time. So volume over pi v t is equal to r squared. So r is the square root of volume in cubic meters, velocity 10 meters per second, and time. And that will give you an answer in meters for the thing. So it's all about knowing the flow. Area times velocity gives you a volume per time. Multiply it by time, now you got volume. If you know you have to pump 100,000 liters through the opening, you can get the time. Or I'm sorry, you can get the radius, or work with the area.
What's the little v? The last one, big is volume.
Big V is volume, and it has more straight lines. Little v is velocity, it has more curvy lines.
Can you explain how you got to that formula?
How I got to this? How I got to this? When we were looking at the equation of continuity, my whole point with these types of problems are, if you know that 5 gallons per second is going in one end, you got to have 5 gallons per second coming out the back end. Water is not going to miraculously appear or disappear. So if A times V will give you a volume per unit time, multiplying A times V times T will give you a volume. If you know that 5 gallons per second is coming out of that pipe, and you run the pipe for 5 seconds, then 5 times 5, 25 gallons has come out of the pipe. So it's kind of you just talk yourself through it. So that means the volume is that flow times the time. And that's how I get it. All right, now, you have a cylinder of steel. Just look for basic iron. That'll be good enough. They're listed all over the place. It is 5 meters high and has a volume of 30 cubic meters. What is the pressure of the cylinder on the floor? So we've learned in Thursday's lecture, it's not the geometric shape of the bottom that matters. All that matters about pressure is the height of the cylinder. So the height is 5 meters. So the pressure is rho steel G times H. So look up the density of steel, density of iron. When I looked online, there were like hundreds of different types of steel. Just go with the basic iron. Gravity and height, and there you got the pressure. The cylinder from the previous problem is resting on a plate of 200 square meters. Now, for something like this, you do need to know what the mass is of this. Density is mass divided by volume, so your mass of steel is the density of steel times the volume. You've got volume, you've got density, you've got the mass. It's sitting on a 200 square meter plate. So it is pushing down with the total force, mass of steel times gravity. Now the question is, what is the necessary force on the second plate to lift the steel cylinder? So I'm looking for F1 if A1 is equal to 10 square meters. So we use Pascal's principle. Pressure on 1 is the pressure on 2. Pressure 1, force 1 over area 1. We're looking for F1. We have A1. Pressure 2, F2 over A2. We have A2. But to get F2, all we need is mass of steel times gravity. So F1 is A1 over A2, mass of steel times gravity. And so that is the force on the left-hand side. That's it. And then that's just Pascal's principle. Yeah. Do I what? I'm finding F1, correct. Okay, number 8.
Force Q is mass of steel times gravity.
Yes. The mass of whatever's on that second plate times the gravity will give you the force that's pushing down. All right, number 8. Now 8 is one of those quick things. We can use the rule of thumb. So for every 10 meters of water, you get 1 atmosphere. Close enough. So at 55 meters, 1 atmosphere per 10 meters, you get 5.5 atmospheres of water pressure. Now, for total pressure, I was a little unclear about what pressure do I want. I would just write them both. 5.5 atmospheres is the pressure due to water. The total pressure is the total pressure of water plus 1, or 6.5 atmospheres. Now 55 meters underwater is a big, 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 big distance for humans with normal scuba tanks. But my brother's done it, but he's crazy.
How far down do you usually go? Because you said you were longer.
Yeah, typically 70, 80 feet. The deepest I've gone is 130. That's because in Guam, Apra Harbor, World War I, Americans came and bombed a German tanker and it fell to the bottom of the harbor. World War II, they came back again, bombed a Japanese tanker, and the Japanese tanker landed right on top. And at 130 feet, you could put your hands out and touch 2 world wars at the same time. It's really interesting. But at 130 feet, you only have about 5 minutes of air because of pressure and.
So you have to go down and then basically come right back.
Yeah, you're not playing around down at 130 feet. So that's why typically it's I hang out at 60 to 70 feet. You can stay down that deep for about 20 minutes. We spend a lot of time at 30 feet, and effectively you could stay at 30 feet for hours. It's not 2 atmospheres of pressure isn't that big of a deal. 4 or 5, because it all comes down to nitrogen entering your blood. And at about 3 atmospheres, it really starts to get in. At 4 or 5, it pours into your blood.
It makes you feel like
Nitrogen narcosis, yeah. I've had a couple of light cases. When you first start diving, they keep you in a controlled environment so that if you do freak out, you've got people right next to you. There was one instance my dad was in the Coast Guard, so he'd get all the horror stories, and there were some people 70, 80 feet down, and one of their friends just narked out and just started swimming for the bottom. And Guam is right off the Marianas Trench, so he got real deep because he just disappeared 27,000 feet down or something. Physics can kill you quickly, but it's fun. But we'll do the fun part of diving on Tuesday. That'll be. But
I remember that from June, when we talked about nitrogen narcosis.
yeah, and also what's worse are the bends. If you come up too fast, if you come up in a regular situation, the gas will bleed out normally through your lungs. Come up too fast, they bubble in your skin, in your organs, in your brain, and that's not fun. So you've got to do decompression
Is
levels.
that because pressure increases the solubility?
Yeah, it increases the nitrogen doesn't get into your blood, but if you increase pressure, it does. It forces the nitrogen into your blood, and if it does blow up in your skin, and it looks like a bruise all over your body, and that's not fun. Sorry to dive. It's story time with Dr. Eschenberg. But he started it. Number 10. Oh no, I take it back. 10, get rid of that. All right.
That's the whole number 8.
Yeah.
So we don't have to look anything else.
For the problem set? No, we got 2 more.
No, like number 8, like that's.
Yeah, that's it. I would say 5.5 atmospheres for water pressure, 6.5 atmospheres for total pressure. Occasionally, I throw a big fat slow ball that just a juicy grapefruit that you just knock out of the park. Number 11. Now this one is horizontal. This one is at a 30-degree down incline or decline. This has a particular mass of 10 kilograms. What I'm looking for is T2 and T1. And this is what we talked about on Tuesday. Now, the one thing that you can ask reasonably is it moving? Answer, no. If it's not moving, it's in translational equilibrium. Sum of the forces in y is equal to x. Sum of the forces in x is equal to, I'm sorry, sum of the forces in y is 0, and this is 0. Now T2 and mg down are in pure vertical or pure horizontal. So 0, you have minus mg, and then this particular T1 gets broken up into its components, T1y and T1x. So T1y is vertical, so plus T1y. Sum of the forces in x, T2 is to the right, and T1x is to the left. So we've set the problems up according to their forces. Now mg is equal to T1y, and T1x is equal to T2. Now T1x and T1y, if I know what that angle is, T1x is equal to T1 cosine theta, and T1y is equal to T1 sine theta. T1y is the opposite side of the angle. T1x is the adjacent side of the angle. So this becomes T1 cosine theta is equal to T2, and mg is equal to T1 sine theta. Here I have two unknowns, can't deal with this. T1 here, one unknown, I can deal with that. So mg over sine theta is equal to T1. Now you can solve for T1. And once you solve for T1, plug it in there, then you have T2. Done and done. Any questions? So the hardest part is recognizing that you're dealing with translational equilibrium and then setting up the sums of the forces vertically and horizontally. And once again, we're breaking down vectors into their components. All right, number 12. We have a sine. This is very similar to problem that we did on Tuesday. We have this distance, 1.5 meters. I'll call that x1. And then I gave you the total length here. x2 is equal to 2 meters. Hanging from the end is a mass of 50 kilograms. The height, or change in y here, we'll call y, is 0.5 meters. I want to know what is the tension of that string. We're going to use the pivot point to be there. So looking at just the bar, that T has a vertical component and it has a horizontal component. The horizontal component does not affect the rotation here because in this plane, the distance from that force to the rotation point is 0. This force will not cause a torque about that hinge. M1G pulls down. So this Ty are the ones that matter. Tx is irrelevant. Is the thing moving? No. So it is in rotational equilibrium. Sum of the torques is equal to 0, which is equal to Ty x1 and M1G x2. In the example in class, x1 was this distance and x2 was this distance. In this particular example, I just gave you there to there and there to there. So the x1 and x2 are a little bit different from how I use them in class. Question?
Can you explain again why TX
Is
is relevant?
it relevant? Yes. So for, not coming after you, so this door has a hinge, and notice how I open the door. I push right here. T1X, as you can see, pushes directly at the hinge. So here's me pushing on that door. It doesn't cause it to rotate. All it does is it increases the force on the hinge into itself. The only way that I can get the force or the door to open or close is to come at it from the sides, this distance. If you drew a line from there to there, they run parallel. So if you drew an imaginary line from this force, the hinge, the side-to-side distance is 0 because it's directly at the hinge. And it would be useless in opening the door. And that's why we don't pay attention to it. No, it's a good question. All right, now, use the right-hand rule to determine signs. Both forces are to the right. Ty is up, thumb out, positive. M1G is to the right and down, thumb in, negative. So this gives you the tension in Y. Now the thing about the tension is it's coming up and to the left. You've got Ty here. You've got Tx there. You've got that angle that I haven't given you yet, but that angle is the same as that angle. This distance here is 1.5. That distance there is 0.5. So tan of theta is y divided by x1, or theta is inverse tan of y divided by x1. So we can get the angle. If you've got that angle, you've got this angle, because two parallel lines bisected, those angles are equal. Sine of theta is ty over t, so t is ty over sine theta. And so that's the tension in the string. And that's it. And we're going to build on this next week with problem 13. But in terms of what we need to talk about, we're done. All the ones that we didn't do today and crossed out will be on problem set 10 with a few more. But other than that, that's it. Any other questions? Going once, going twice. Enjoy the game.